Hello, everyone. Good afternoon and good morning. Welcome to the new Hypatia Colloquium. I heard some noise on the background. Don't worry. So this is it's a pleasure to introduce you to the new event, and please allow me to congratulate once again with the speakers of today and the speakers that have so far gave us the talks. We are very proud and very enthusiastic about what witnesses on all the science that has been done by you, by the early career astronomers these days, despite of the difficult times that we are all going through. Just from my side, only very quickly, just to mention that again, so there are two ways to attend this series. On one side, you can attend via Zoom. Basically, if you register on our web pages, you can, on the Hypatia web pages, you will receive basically an hour before the start of the event, you will see a dedicated link through which you can attend the event with us, basically virtually from Zoom, and you can make questions at the end of each session, basically by directly to the speakers. While for people attending on Zoom, on YouTube, they can also make questions, send their question to the speakers using the live chat. And we will, and if the speakers they are not able to, because the time is running out, they will not answer immediately. But this is good that you still post your chat, your question on the chat, because they can address them later during anyhow, the talks will stay online for later views. Also, please be reminded that you can always, if you go to our pages, again, to the Hypatia pages, and you look at the program, you will see that for each of the speakers, there is a link to a PDF where you can download the CVs of our speakers, and so you can also get in touch with them and see how their history and their work in more detail. And finally, if you also are not comfortable with making questions using the chat on YouTube, there is also a third way, which is you can use. There is, again, on our pages, there is a questionnaire that you can fill in. You can click submit, and basically we receive the question directly by email, and then we can pass it to the chair of the session and start, and they can also pass them to the speakers. Having said that, in fact, let me say that I'm very grateful to the chair of today's, which is Paolo and Dominica. They are a fellow and a student of ESO. We are very happy and grateful to, of course, to our youth students and fellows of ESO, that they are all volunteering to chair these sessions, because they are making the entire event even more exciting and enthusiastic thanks to their energy. And so thank you very much. And today I would like to, again, so thanks them. And I will give the floor to Paolo to make an introduction. And thank you very much, and enjoy the event.
Thank you, Giacomo. Can you see my video cam?
Yes, we can see you and hear you. Yeah, perfect.
Okay, thank you. So hello, everyone, and welcome to our Hypatia Colloquium. My name is Paulo Miles Paez, and I will be co-chairing this session with Dominica Itri. And I cannot switch. So for today, we have 2 talks, and it's my pleasure to introduce our first speaker, who is Eloisa Poggio. She is currently a postdoctoral researcher at the Observatoire de la Côte d'Azur in France, and previously she did her PhD in the Observatorio Astrofisico di Torino in Italy. And today she's going to talk about evidence of a dynamically evolving galactic warp. So Eloisa, whenever you're ready, please share your screen.
Right. Okay, can you see my screen?
Yes.
Okay. Good. So good afternoon, everybody. Thanks for coming. I'd like to thank the organizer for giving me the chance to present our results today. So I'm going to talk about our galaxy, the Milky Way. So there will be a brief introduction, and then I will present our observational results, and then our interpretation and our conclusion. So let's start with the introduction. So this is what we think our home galaxy, the Milky Way, looks like. So we think that we live in a spiral galaxy. Of course, we know that galaxies in general are complex systems, and several physical processes are shaping their evolution. Of course, our own galaxy can be used as a benchmark for understanding external galaxies, and that's because we are right inside it. The solar system is embedded in the galactic disk, where most of the stars in the galaxy are contained. So we have a spatial perspective, and we can study the galactic system on a star-by-star basis. Recently, the Gaia satellite measured the positions, parallaxes, and proper motions for more than 1 billion stars. And so that we can derive distances, we can derive three-dimensional velocities for the stars using also radial velocities. So this means that we have a great wealth of information, and we can study in great detail an unprecedentedly large portion of the galactic disk. So we know that the sun is located at approximately 8 kiloparsec from the galactic center. So we see a portion of the disk, and we can use these precise measurements of the stars in our galaxy to understand something more about the physical processes that are currently taking place in our galaxy. So this talk will be dedicated to a feature which is called warp. It is a large-scale distortion of the galactic disk. So here you can see the inner parts of the disk, which are flat, and the outer parts that are warped with respect to the inner parts. So here the disk is bent upwards, and in this other region, the disk is bent downwards. So we call this feature galactic warp. This feature has been discovered in 1957, so a long time ago. And then after that, astronomers found that actually this is a very common feature also in external galaxies. So actually spiral galaxies are usually warped. So this means that warps are either long-lived features or they are frequently regenerated. But in any case, the mechanism responsible for the origin and persistence of warps in these galaxies is unclear. So if you have a galactic disk, you can warp it in several ways. For example, you can have a torque from a dark matter halo, or you can have an interaction with a satellite galaxy, or a misaligned inflow of gas, or intergalactic magnetic field. So we have a huge variety of models that can explain warps in general. But of course, we don't know, or at least before Gaia, it was not possible to put constraints on which model is at work in our galaxy. And that's mostly because it was not possible to have information on the kinematics of the stars. This is very important because if we know how the stars are moving, we can put some constraints on the warp, as you will see in a moment, in a couple of slides. We will be able to model it, to put some constraints and learn something more about the origin of this large-scale distortion. And as a consequence, we can learn something more about the evolutionary history of this warp and of the galaxy in general. And that's why we need high precision astrometry. This is only possible if we are able to measure and to assess what the stars are doing inside the galaxy, and we are able to compare the data with the models. So let's start with a very, very simple model. We have here the center of the galaxy. We have stars rotating around the galactic center. This is called galactic rotation. We know from observations that the solar system is located to the line of nodes of the warp. The line of nodes is the transition between the positive and the negative vertical displacement. So if here we have z, the vertical coordinate positive, greater than 0, here z less than 0, and here we have z equal to 0 everywhere. Of course, the line of nodes doesn't have to be straight, but we start with this simple model as a starting point. And so let's put the sun close to it. And yeah, so if we have stars rotating around the galactic center like this, if we have a flat disk, so no warp, all the stars will have their own peculiar motion, of course, but the mean vertical velocity will be 0 everywhere. But if we have a warp, then stars will typically go up and down, following the warped disk. And this means that there will be a place with a maximum vertical displacement and another place with a minimum vertical displacement, or maximum with an opposite sign. So if we look at the velocities, we find that actually we expect the vertical velocity to be maximum here close to the line of nodes, and then 0 here at the top of the warp, and then maximum but with an opposite sign on the other side of the galaxy, which we don't see, of course, and then 0 again. And we can easily understand that if we compare this to an harmonic oscillator, where we have a 90 degrees shift between the spatial displacement, spatial coordinate, and the velocities. Of course, we can obtain a similar result in a more elegant way if we assume that our galaxy is a collisionless system where stars are moving under the influence of a smooth potential. And so we apply the collisionless Boltzmann equation, and then we put our warped disk into the collisionless Boltzmann equation, and we derive the 0th moment, so that we are able to predict a trend for the vertical velocities. And what we find is that actually the vertical motions are expected to be maximum in proximity of the line of nodes here, like this. So something like this. We expect to observe a signal similar to this one. Moreover, the signal is expected to be larger in the outer portions of the galaxy, and that's because the warp is larger in the outer regions of the disk. So in other words, this is the signal that we are expecting. So we want to observe an increase of the mean vertical velocities toward the outer portions of the galaxy. So the goal of this talk is, first of all, to detect the signal, which is the signal that I'm showing you here. So this increase in the mean vertical velocities. And the second goal is, once we have detected the signal, to model it and to try to interpret what we find. Okay, so let's start with the data. We selected 2 samples of upper ring sequence stars and giant stars, which have typically different ages. Upper main sequence stars mostly contain all B stars, so they're typically young. The giant sample contains 12 million objects, so it's a giant sample of giant stars. And right, so the first test that we made was to look at the spatial distribution of the 2 samples. So in the following, I'm going to show you some plots. They all have the same orientation. So the sun is located at the center of the plot, this black cross. The galactic center is to the left. The outer regions of the galaxy are to the right. And the galaxy is rotating clockwise. Okay, so let's start with the giant sample. Here, points are color-coded by the number of stars. And as you can see, the number of objects is decreasing as a function of galactocentric radius. So this makes sense. We expect to have less stars in the outer regions of the galactic disk. This is perfectly expected from an exponential disk. We have also another effect which is taking place. So the number of stars is decreasing as a function of heliocentric distance, and this is expected from a magnitude limited sample. So this plot is a combination of these 2 effects working together. And yeah, so we can say that the giant sample exhibits a smooth distribution, whereas the upper main sequence sample looks a bit different. We see these red bumps, these blobs here, which we believe are segments of the nearest spiral arms. Right, so this slide is a bit off topic. It's a short digression from the main topic of this talk, but it's a follow-up to this image that we obtained in 2018, and using the same sample but more recent data, we used a slightly more sophisticated technique. Instead of just plotting the number of objects, we used a unsharp masking technique. So we are comparing the local number of stars for a given point with the mean density in that region, and we find that all these red bumps here, so these clumps, indicate the position of the spiral arms in our galaxy. So these are clumpy but coherent arches that could be interpreted as arms. So for example, this is a Perseus arm. This is a local arm that we find to be much longer than previously thought. It ascends at least 8 kiloparsec. And then we have the Sagittarius Carina arm, and where the color code is not helping a lot, but this might be separated from this Sagittarius Carina arm. This might be the Scutum arm. So this is just to say that indeed we are seeing a signature of the spiral arms in our galaxy. And indeed we have two different samples. So the upper main sequence sample, which mostly contain young stars, and the giant sample, which typically contains dynamically older and more relaxed stellar population. What happens if we look at the vertical velocities? So what we can see in both samples, we observe an increase of the mean vertical velocities in the outer portions of the galaxy. So as you can see, of course, if we had a flat disk, we would have green color everywhere, would be zero everywhere. But here we have a gradient, right? So we interpret this gradient in the mean vertical velocities as the signature of the galactic warp. Or in other words, the stars are feeling that the disk is warped, and we see the signal associated with it. And we detected this signal with a significance, with a signal to noise ratio greater than 10. Right, so let's now try to model this signal. So let's remember this simple idea that we have this peak close to the line of nodes. So here we have proper motion, which is a proxy for the vertical motions. Of course, we don't measure velocities, we measure proper motions. And then we have the galactic longitude here, and we have this peak. This is approximately toward the galactic anti-center. So this peak is the signal that we want to analyze. So what we did was to construct a model for the galaxy. The model includes a model for the spatial distribution of the stars in the galaxy, a model for the kinematics, so galactic rotation, asymmetric drift, whatever, all together. Of course, we model also the warp spatial geometry. So we assumed this geometry, which works well for RGB stars, which is consistent with our giant sample, but we also tried with other works using different tracers, as you can see here. So we explored several options. And what we found is that, the models also takes into account the selection function of our sample. So we put all these things together, and we find that, if we compare the signal in the data with the prediction from the model, if we assume that the warp is static, so that stars are rotating like this, but the warp is fixed, frozen in time, it's not moving, then the signal that we obtain is much larger than the one that we observe in the data. So we asked ourselves, what can we do? Of course, if we have a static model, we have no kinematic parameters, right? So this is the simplest model one can have. But if we add, for example, one parameter, so we say, right, so the warp is not static. The warp is moving. And we assumed that the line of nodes is moving as a function of time. So something like this. So the inner parts of the galaxy remain relatively unperturbed, whereas the outer parts are moving like this. So we add only one parameter, which describes basically this is what we call precession rate. It's basically the pattern speed of the warp. So how fast the warp is moving. And if we add this new parameter and we fit for it, we are able to match the data much better. So in other words, if we use this model, we can explain the data much better, and we obtain a precession rate of almost 11 kilometers per second per kiloparsec. And this value was recently confirmed also by another group with an independent data set. So the two values are consistent within the uncertainties. Right, so I guess we can summarize this part of the talk by saying that if we compare the signal that we observe in the data with the prediction from a static model, we don't find good agreement. So instead, we propose another model, which is, of course, very simple. There's only one new parameter that we introduce. The parameter is called warp precession, and it is the angular speed of the warp, and it tells us how fast this warp is moving, like this. The warp is moving, but the stars inside it, the stars inside the galaxy, will move at a different speed. For example, this yellow dot that you can see here is a star located at approximately the sun's location, so at approximately 8 kiloparsec from the galactic center, which is moving at the typical speed of the stars in a solar vicinity. So this is actually, this is showing galactic rotation, which is approximately 30 kilometers per second per kiloparsec, whereas the warp is moving at approximately 10 kilometers per second per kiloparsec. So the warp is a bit slower, right? A bit slower than galactic rotation in general. But this warp precession rate that we found is significantly different from zero. So if we compare our result to the prediction from other models, we find that if we assume that the warp is a result of the assembly history of the galaxy, we would have a very, very small precession rate like this, which would be consistent, given our uncertainties, would be more consistent with a static warp, so with a very long period. Whereas warp precession rate of about 11 kilometers per second per kiloparsec could be explained by a recent or ongoing encounter with a satellite galaxy. So to date, the only model that can explain these results, so these pattern speed of the warp, is an encounter with a satellite galaxy. So for the moment, at least, we have to exclude the first scenario. So we have to say that the first scenario would predict a very slow precession rate, whereas we're measuring something much faster. And so what we did was to ask ourselves, okay, what happened if we look at the response of the galactic disk to an infalling satellite? So we have a satellite moving on its orbit. This was a paper from 2006 from Weinberg and Blitz, where they looked at the response of the galactic disk to the Magellanic Clouds. So you see that the satellite is moving and the disk is responding with this very complicated behavior, right? Of course, the response is much more complicated than our what our model predicts, of course. But in some places, for example, if we look at, if we look at this place here, like this, the disk is doing something similar to what we saw before, right? So it might be that the simple model, which is right, it's not meant to describe something as complicated as this, but might be an approximation, right? So we might explain the motion of the galactic disk using a simple model that approximates both in space and time. In space, because we don't see the entire galactic disk, we only see a portion of it. And in time, because we don't expect the warp to precess at this angular speed forever, of course, it will be only an approximation of something more complicated in the case of an interaction of a satellite. But it might be that we are understanding a bit more about what the disk is doing. So what we did was to use n-body simulations of the galactic disk interacting with the Sagittarius dwarf galaxy. I forgot to mention that possible candidates to generate the warp in our galaxy are the Magellanic Clouds or the Sagittarius dwarf galaxy, because they are the most massive ones. So these are two possible culprits, I would say. And if we look at the motion of the warp, we find that the warp is indeed moving in a prograde direction, so in the same direction as galactic rotation, and quite fast. So very similar to what we measured using our kinematic model, which was describing the data. So we find this behavior when the impacts of the satellite are more frequent, or in general close to an interaction. And the motion of the warp is slowly retrograde in the most quiescent phases. So of course, in these two cases, I would go for this one, for the first one, because this one would be more consistent with what we see in the data, or could, I would say that it could possibly give an explanation to what we are seeing. So this might be a dynamical interpretation of our results. Right, so to summarize, so this is my last slide. So the first point was to detect the signal associated with the warp. So we find that indeed we can detect the signature of the galactic warp using the motions of the stars in our galaxy. We find that if we try to model this signal, the warp is not static. It is an evolving feature. It is a dynamically evolving feature. And we propose a very simple model that might be, of course, improved in the future. This model has only one new parameter, which is called warp precession. And if we assume this parameter, then we can measure the angular speed of the warp, which we call warp precession rate. And we find that it is about 11 kilometers per second per kiloparsec. And if we compare this value with other models, and especially with a simulation of the galactic disk responding to an infalling satellite, we find that indeed the warp precession rate, or the warp pattern speed, has a constraining power in the context of an interaction, and fast as we measure like this, close to an interaction with a satellite. So I think our results are suggesting that indeed our disk, the galactic disk of our galaxy, is a very interesting and complicated feature where a lot of physical processes are at work. And we are now able to compare large data sets, compare them to the models, and try to understand something more about the evolutionary history of our galaxy. So this is the end of my talk. Thank you for your attention.
Thank you very much, Eloisa, for this nice talk. Also, thank you for being so strict to time. And we already have one question in the chat of the Zoom.
Okay.
So Loreto Barcos Munoz, do you want to unmute yourself and make your question?
Yeah, thank you. Yeah, I think it's better. Sorry, I asked that question very early in the talk. I was like very anxious at that moment, but I think it's still relevant, and great talk, by the way. It's great, gorgeous data, excellent analysis. I guess the question would be, I wasn't clear if, maybe I was confused. Do you use data from the other side of the galaxy? Because at the beginning, for the first part of the first conclusion here, you use mostly nearby stars, right? And
Yeah.
I guess, we shouldn't expect to be things so different on the other side, but I'm wondering, if you use data.
Yeah. Well, we mostly see, stars on this side of the galaxy because, there's the bulging side. So this is quite complicated. So we see only a portion of the galactic disk. And of course, for example, like this. So the galactic center is located in 0. So X is 0. So it would be something like this here. So we are basically analyzing this region, which, I understand that it looks like a small region, but compared to previous data sets, it's much more than we had before. And we don't use stars on the other side of the galaxy because, even if we have some stars on the other side of the galaxy, those measurements will be, maybe the precision wouldn't be good enough. And so we prefer to only look at the regions where we have good sampling. So we have a lot of stars and we have good measurements.
Thank you.
Also, Laura Corsi says in the YouTube chat that it was a great talk. I also have a very naive question. I'm not working in this field, and maybe you mentioned it, but I miss it. So you've been talking about Gaia DR2. So what are your expectations for the new data releases?
Yeah, so I talked a lot about Gaia DR2. Actually, there was the latest release is the early data release 3. Which took place in December 2020, where we had improved astrometry with respect to Gaia DR2. So better measurements for parallaxes and proper motions. There will be another release very soon, I think in 2022. We still don't know the date. But there will be also something very interesting, which are the stellar parameters. So we will have, effective temperatures, surface gravities, radial velocities for more stars. So metallicities. We will have a lot of information for several objects. So much more than what we have now. So this will be very interesting, I think.
For sure, yeah. So we also have Ilsan John, who wants to make a question. Ilsan, please unmute yourself.
Thank you. Thanks for the very nice presentation. Because time is limited, I want to ask I have several, but I want to ask 2 questions. So first one is, you showed the vertical velocity as a function of galactic longitude and show that there's a velocity bump, but the data themselves actually shows not only a single bump, it looks like there are multiple. So do you think this is it related with the fact that the warp itself is not the rigid, the patterns, or is it's a different, difference for the warp precession speed? How realistic is the warp structure, not the solid rigid body, but the differential velocity, the rotations of the warp is realistic?
Yeah.
That was my first question. And the second one is kind of related with that. Do you find your stellar velocity, the stellar warp matches the H1 warp?
Okay, so I'm going to start with the first question. So yes, I agree that the data are more complicated than our simple model. And I also agree that in the future, we might, improve this model to explain a bit better the data. For example, if you look at these maps, especially for the upper main sequence samples, you have all these bumps here, right? And of course, all these bumps are not captured by our model. And this is clear, I think, especially for the young stars, which are dynamically colder. And of course, this is something that in the future we want to explore. So we started with a very simple model. And you're right, the rigid model is just an approximation. So it's just a starting point, but we want to do something better in the future. And of course, it's possible to make it more sophisticated and, closer to, of course, nature is more complicated than our model, our simple model. So I guess in the future, we might want to study this as well. Some bumps could be, just noise related to the data, but other bumps could be real and could be associated with, bending waves in the disk, or there are several interesting phenomena which might be taking place as well. So yeah, so that was for the first question. The second question was, sorry, I forgot.
So match between stellar warp disk and H1 warp disk.
Yes. So this is not clear actually, because I don't think I have the plot here, because some works find a good agreement with the neutral hydrogen, because the warp was first discovered in neutral hydrogen observations, and some work found good agreement. Other works found that the amplitude of the warp in the stars was less prominent compared to the gas. For example, in this paper, Robin 2009, and also the Rayleigh, which I forgot to mention here, another paper from Céline Rayleigh, they compare the amplitude of the warp in the gas, in the dust, and in the stars. And in that paper, they found that the dust is somehow intermediate between the amplitude of the warp in the stars and in the gas. And so we have these slightly different amplitudes depending on the tracers. So that's why also we tried, different works, because there's no unique answer to these questions. So we try to explore all possible options. So it might, yeah.
So I just last quick question. I was more or less interested about the phase. Does that phase match? Not the amplitude.
Yeah. So I think most of the works, most of them agree that the line of nodes is close to the sun. I think within, I would say, 15 degrees, maximum 20 degrees from zero. For example, if I go to this, yes. Sorry, was too fast. Okay, so this is phi equal to 0, right? I think most of the works place the line of nodes approximately here, here or there. Some works also on the other side, but the difference is really a few degrees, so a few tenths of degrees. I would say within 15 or 20 degrees from phi equal to 0. So it should be more or less there.
Thank you very much.
Good. So we have the last 30 seconds for Dietrich question, please. And then we will move to our next speaker.
Yeah, great work, great talk. Since this is a gravitational effect, can one use the warping to constrain the gravitational potential of the Milky Way, and in particular the amount of dark matter?
That's a good question. I have to think about it, because we derive our model using the zeroth moment of the collisionless Boltzmann equation, which is a very simple model, and it doesn't even assume a specific galactic potential, right? So so from what we have now, I would say maybe not. But maybe in the future, if we develop a more sophisticated model, I think it would be useful. It would be helpful somehow, because, you know, this is, like you said, it's a gravitational phenomenon, at least based on our results. I would say that if it's a gravitational phenomenon, we should be able to learn something more. For example, there are several works showing that the precession rate the precession rate of the warp is related to the shape of the halo. So if it is prograde or retrograde, so if it is prograde, you have an oblate dark matter halo, whereas if you have a slightly retrograde precession, then the dark matter halo would be oblate. So there's some connection. But of course, if you have an interaction with a satellite, this will make things much more complicated and things will move much faster. But I agree that there's a good connection, a strong connection. This might be explored further in the future.
Yeah, very exciting. Thank you.
Thank you very much. Unfortunately, we don't have more time for questions. I apologize to people that make questions in YouTube. I really encourage you to contact Eloise and keep discussing offline. And now I would like to give floor to my co-chair, Dominica, and who is going to introduce our next speaker. Thank you.
Thank you, Paolo. And hello, everyone. My name is Dominica, and I am a student in ESO. It is my great pleasure to co-chair this session with Paolo. Our second speaker today is Belen Alcalde. She is currently an ESO Alma Fellow. She obtained a PhD degree last year at Universitat Complutense de Madrid with thesis about first massive galaxies formed in the universe. Her research interests cover galaxy formation and evolution across cosmic time, massive high-redshift galaxies, stellar properties, multi-wavelength observations, especially those within sub-millimeter range, as well as machine and deep learning techniques. Today, she will try to answer the question, if we are missing massive red galaxies at redshift higher than 3. Belen, the virtual floor is yours.
Okay, thank you very much. Can you see the slides?
Yes.
Okay. So hello, everybody then. Thanks a lot first for the introduction, Dominica, and also for giving me the opportunity to present my work within this colloquium. And as you just mentioned, as we do not have much time, I'm going to start by basically raising a question. And the question is, are we missing massive red galaxies? And to help to answer these questions, I will first give a general introduction to explain the context from which this question arises. I will then explain how we can identify this population of galaxies, and I will prove the existence of a massive population of red galaxies at high redshift. And also we will analyze their number density and their role within galaxy evolution to end up stepping into the future. So let's start with why. The main driver is the need of understanding how, basically the process of the formation and evolution across the history of the universe that the most massive galaxies have gone through. So if we go back to the very beginning, as far as we know, the universe started 13.8 billion years ago, and after a long evolutionary journey, it has given rise to our neighborhood, so this local universe. And the local universe is characterized mainly by two types of galaxies. So we have spirals, which are blue, young, active, disky-shaped galaxies. And we also have ellipticals. And ellipticals are red galaxies, spherical galaxies, hosting very old stellar populations. So this means that they are kind of dead, not forming stars anymore. And they do indeed correspond to the most massive galaxies that we know. It's also important to note that our current understanding of the universe is mainly based first on the lambda CDM model and also in the hierarchical growth of structures. And while this model has been proven to be very successful in explaining mainly the early phases of the universe, recent observations are also revealing certain weaknesses. And I want to highlight that according to those observations, the most massive galaxies seems to have appeared very early in the history of the universe and through very violent and rapid processes. And in this sense, if we want to shed some light into this problem, as well as the archaeologists will, in their attempt to understand the evolutionary trees that the current species have gone through, will search for fossil records of their ancestors. Something that we can do is to search for and quantify the number of ancient galaxies that populated this early universe. And that's indeed what I'm trying to do, to gather a complete sample of those massive galaxies that live in the early universe. And while it is true that there are already many studies that have reported the existence of this massive population of galaxies at very high redshift, as proven by this stellar mass function from Gracian et al. Back in 2015, the stellar mass function is unfortunately still poorly constrained at redshift higher than 3. And the reason for that is that most of the results are coming for either optical or ultraviolet selected samples. And these samples are biased against optically faint galaxies. And this means that we might be missing a substantial population of optically bright but infrared, optically faint, but infrared bright sources that are not even in those more complete catalogs that are available today. Another very powerful and widely used tool to try to understand galaxy evolution are simulations. However, when we try to compare the simulated and the observed stellar mass function, certain discrepancies arise. And those discrepancies are especially larger in the low and the high mass end of the stellar mass function. And that is critical to us in the sense that we are searching for the most massive galaxies in the early universe. We think that those discrepancies might be linked to those merger trees that are used within simulations in order to assemble the most massive galaxies. And without going into detail here, just to mention that for those merger trees, it's extremely difficult or even impossible sometimes to build galaxies with more than 10 to the 11 solar masses, so very massive ones, at redshift higher than 3. And hopefully by this point of the talk, I have already at least convinced you about the importance and the need of searching for this missing population. And thus I'm gonna jump into the procedure to understand how we can identify this population of galaxies. For that, what we have done is to compare the deepest available images from the Hubble and the Spitzer space telescopes, using basically a color selection or a dropout technique in which we are searching for, as I mentioned, optically faint, so galaxies which are not detected even in the deepest images from the HST, but which are bright at least in the 2 bluer IRAC bands. This method is based on the fact that at redshift higher than 3, there are 2 spectral features, namely the Balmer break and the 4000 Armstrong break, which are obviously redshifted, and this means that they will lie in the wavelength range between the H band and the IRAC bands. Due to the selection technique, I will be calling these galaxies Balmer break galaxies, so BBGs. But I also want to mention that they have recently become famous as dark or HST dark galaxies. So if you are close to the topic, I just wanted to clarify that we are talking about the same kind of objects. And in order to compare IRAC and HST images, given the very different spatial resolutions, we use a frame in which the high resolution H band is convolved with the IRAC PSF, and the flux is scaled to match IRAC fluxes. This means that this frame is going to be basically how the H band would look like with an IRAC resolution. And we also use the residual frame, which is obtained by subtracting this convolved and scale image from the IRAC raw image. This means that in the residual template, only near infrared bright but optically faint galaxies will remain. So those are indeed the galaxies that we were looking for. And using this procedure, we found 33 Balmer break galaxies. These might not look as a lot, for especially if you are studying very low redshift galaxies, but it is a lot, and it's extremely important, and we will prove it later. And just to say that half of the sample is located in the good north field, while the other is in the good south. And by this point, you might be wondering already how those galaxies look like and which are their physical properties. Here we have an example of one of the VBGs, maybe the only one that I can use to show up in an Hypatia Colloquium, and in the sense that it's probably the VBG with highest signal to noise and also with larger spectral coverage. So it's not only detected in the mid-infrared, but also in the far infrared and even at sub-millimeter wavelengths. This is extremely convenient because we can use dust emission models to fit its photometry from the far infrared to the radio wavelengths, and not only constrain its properties, but also, and more importantly, to obtain reliable star formation rates. However, life is not as easy as it seems, and when this sample was analyzed, only 5 of the 33 vulnerable galaxies had some far infrared emission available. So then, if I want to be honest to you, most of the galaxies in the sample do instead look pretty much like this one. So we would have 1, 2, 3, 4, 6 at most reliable fluxes and a bunch of upper limits. This means that the deriving physical properties and the characterization of these galaxies itself is extremely challenging. For that reason, analyzing the location of these sources within color diagrams can help understand their nature. And here I'm showing on the right, the UVJ rest frame well-known diagram, and also in the left, the H-3.6 versus 3.6 diagram. I want to highlight here that in the y-axis, this color basically mimics our selection criteria. And if we first analyze where the general population of galaxies lie within those diagrams, this is catalog galaxies with more than 10 to the 10 solar masses at redshift higher than 3. We can see that they basically present blue colors in both diagrams. And for comparison purposes, we've created a color selected sample based on the H-3.6 color, which has to be larger than 2.5 magnitudes, meaning that for sure in this diagram, they are gonna be red galaxies. But the important thing is that those colors translate also into red colors in the UVJ. And this gives us some information about the sources, which are probably gonna correspond to either very dusty or highly star-forming galaxies. And what happens with this new population of VBGs? So VBGs also have very red colors in both diagrams. They indeed populate a very similar region as the color selected sample, with the main difference being that they are slightly fainter. And by this point, you have basically believed me when I claimed that this population was composed by very massive high redshift galaxies. But in fact, the effectiveness of the dropout color selection criteria can be proven using both the redshift and mass histograms. And here I'm showing the distribution of the general population, and we can see how they peak basically at the selection cuts, so at redshift 3 and mass of 10 to the 10 solar masses, and then they exponentially decrease. While the color selected sample, and here I want to clarify and make sure that you understand that we haven't implied any redshift or mass cut into these samples, but they still have very high redshift and larger masses, and they indeed peak at a slightly larger both redshift and masses. And again, what about the VBGs? So they, as expected, or at least as I was expecting, they saw a very similar distribution as the color selected sample. And we can see that we are more effective at selecting galaxies with more than 10 to the 11 solar masses between redshift 4 and 6. Other very relevant physical property of galaxies is their ability to form stars, and that can be easily seen in the star formation rate versus mass diagram, where most star-forming galaxies seem to lie in the so-called main sequence. And we can divide this diagram into starbust, the main sequence, and sub-main sequence galaxies, according to their location with respect to the main sequence. And if we do that, what we find is that 20% of our sample is located above the main sequence, so it's basically a starbust. And it's also worth noticing that all the far infrared emitters do also correspond either to starbust or star formation rate lower limits. Then half of the sample is located within the main sequence, and 30% lie below the main sequence. And if we analyze the position of these three star formation rate modes within the UVJ diagram, it is obvious that the vast majority of the sources do correspond to dusty star-forming galaxies. This means that they are located in the left part of this diagram. And we have several, also it's important to notice here that also the far infrared emitters are located within the dusty star-forming region. While we find several blue star-forming galaxies that correspond to the less massive main sequence galaxies, because here the symbols are scaled with the mass. But I want to point out that while we only find 3 galaxies within the quiescent wedge, there is a bunch of sub-main sequence galaxies, some of which only have a U-B lower limit, which are still compatible within the large uncertainties that we have with being evolved galaxies. And by this point, I want to recap a little bit, first by highlighting that we have proven that these selection criteria translate into a redshift and mass selection, and also that the VBGs, which obviously resemble the color-selected sample, correspond mainly to dusty star-forming galaxies, while we cannot rule out the existence of evolved galaxies within the sample. And now in the last part of my talk, I'm gonna focus in the most relevant question, which is nothing else but which is the importance or the contribution to galaxy evolution. And for that, here I'm showing basically the evolution of the number density of galaxies with more than 10 to the 10 solar masses. This is how many galaxies with more than 10 to the 10 solar masses we have at different epochs. And if we look at the number density of the general population, so what we have been calling the mass limited sample from Candace's catalogs, which is shown here with empty stars, we can see that it agrees pretty well with the literature, so it's compatible. And adding the VBGs, this new population, as shown with the field stars, basically slightly increases the number density. Indeed, they account for around 10% of the general population, depending on which redshift range you are considering. And it's also important to check how the models behave, and we can see that Illustres and Eagle, shown with the green and red lines, do a pretty good job in order to reproduce observations up to redshift 4, 5, and even further. However, through this talk, we have learned that these new populations is mainly composed by very massive galaxies with more than 10 to the 11 solar masses. And if we focus on that very massive population, then this new population turns out to be very relevant. Indeed, they correspond to more than 30% of the general population of galaxies, of massive galaxies, between redshift 4 and 6. And indeed, also, if we only account, if we only take into account the red galaxies, they would be even larger. The percentage would be as large as 50%, meaning that they represent half of the population of massive red galaxies at high redshift. Additionally, if we focus in the right y-axis, which represents the local massive galaxies that were already in place at a certain redshift. So this is the fraction, basically. What we find is that 3% of the local most massive galaxies should have assembled more than 10 to the 11 solar masses only 1.5 gigayears after the Big Bang. And these numbers represent a real challenge for current models of galaxy formation and evolution. Indeed, when comparing these results with simulations, the discrepancies between simulations and observations become obvious, while Eagle is unable to reproduce the number of very massive galaxies in the early universe. Illustris do it much better indeed, but it plumbs between redshift 3 and 4. And while it is true that there are other studies that using the Millennium simulation, which has a larger volume and semi-analytical models that are able to find some galaxies with more than 10 to the 11 solar masses, while not more than 10 to the 11.5 and not at larger redshifts. If we look at the difference between those models, they are of orders of magnitudes. And this clearly reveals how important it is to accurately constrain the number density of these massive galaxies at high redshift if we aim to understand the process of galaxy formation and evolution. And to sum up some of the results, I want to highlight some ideas. First is that BBGs represent more than 30% of the most massive population. And also that those number densities imply that 1 of every 13 very massive galaxies in the local universe should have assembled more than 10 to the 11 solar masses in the first 1.5 gigayears of the universe. And these results, as I have mentioned previously, is extremely challenging for state-of-the-art simulations. And as I've been summarizing the main points of the talk, I just want to give you some perspective, and you might be wondering what comes next. So regarding the next steps to be followed after this research, the most obvious one is the follow-up of the sources to first confirm the redshifts, and so that you can later on go and take a very expensive spectra with very large telescope and get some understanding of their star formation histories. And in this sense, it's also worth noticing that Wang et al. Presented a similar sample of optically faint galaxies in different cosmos fields, which present continuous observations in the submillimeter wavelengths. And while this is not enough for constraining the redshift, it's definitely a step in the right direction, and it can help us to better constrain their properties. And more relevantly, they could spectroscopically confirm the redshift of 2 galaxies within the cosmos field. So this means that we are not just in the right direction, but also in the right path. So give us some hope. And that, together with the recent announcement of ALMA return to operation, it's time to definitely be optimistic, as those new observations will surely help us to better understand this population of gigantic creatures that live in the early universe. And with those good news, I want to open the floor for any questions or comments that you may have.
Thank you, Belen, for your wonderful talk. Yes, I would like to invite our audience to ask questions. And I see that Ilzang Yun already has his hands raised. Please, Ilzang, go ahead.
Thank you for the very nice talk. I'm a bit confused. So in the beginning of your talk, you mentioned that you're looking for the massive sort of the passive elliptical type galaxies. Then you mentioned to find out those population, you use the AHS, the H-band, and smoothed by the Spitzer PSF, then subtracted those smoothed the images from the Spitzer images, trying to find out the excess emission. That indicates somehow the HST dark galaxies. But I was wondering, how do you know that is actually the elliptical-like galaxies, not the very massive disk galaxies?
What, can you repeat the last sentence?
So how from those residual images between the HST and the picture, you find out the excess emission, which indicate HST dark, the H-band dropout galaxies.
Yeah.
Then my question is, how do you know these galaxies actually the massive elliptic galaxies, not massive disk-like galaxies?
Yeah, very good question. Maybe it's that I haven't explained it well. So what we are trying to understand is basically how those monsters, those elliptical galaxies that live in the nearby universe did actually form. And for that, we go and search for very massive galaxies in the early universe to see if they exist and how early they can appear and which are their properties. And we first analyze and go for those galaxies that we know that are massive, very related with the Iraq brightness of these sources. And then we try to characterize them. But that doesn't mean that they are ellipticals. Indeed, most of them seem to be very dusty star-forming galaxies, as I mentioned, so very dusty galaxies, but with a lot of star formation going on, as it has been proven also by submillimeter observations. So they are very active, but it's true that we can't rule out the possibility of that some of those galaxies have already quenched or are in a phase in which their star formation is going down and they are not that active anymore. Because for some of the galaxies, that is the possibility that, according to the observations, seems to be more feasible, but it's a very tiny amount of them. Most of them seems to be very active indeed.
Okay, thanks for the clarification.
Thank you. So while we are waiting for other questions, I will ask one from myself. You mentioned that Alma will help you to study this subject in deeper. I was thinking about other powerful instrument that we are looking forward to be launched. So how do you think the GWST will help you to study those sources or increase the number of BBGs?
Yeah, I mean, James Webb is going to be critical for this kind of objects, definitely, because it will provide us with spectra in larger wavelengths, which right now is not available, and with very high signal to noise, meaning that we will be able not only to find them, because I'm sure that we will find more of them once it's launched, but also to properly understand and constrain their star formation history. So at that point, it will be much easier to answer the last question, whether or not they are active or passive galaxies, and to better understand also their metallicities and many other things that right now, with such a little amount of information, is kind of hard. So yeah, really looking forward for it.
Of course. I see Paweł Krupa has a question. Please go ahead.
Hello, I very much enjoyed your presentation. It's really exciting material. Do you have a reference for the figures which were showing the star formation versus mass? Where you went, I think you had even star formation rates surpassing 1,000 solar masses per year, right?
Yeah, I mean, that is part of my work. Indeed, that image should be in Belen Alcalde Pampliega et al. 2019. So you should be...
So it's your name, 2019? Okay, so I can find it on the ADS, because it's really very impressive. And also what you pointed out, you are confirming the downsizing problem, right? And you know that Francesca Mattiocci actually, as far as I understand it, pioneered this whole thing, right? I mean, I think she was the first one to actually point out that there is this stress, and that these ellipticals we observe must have formed quickly and early. That's very impressive, and it's also impressive that the latest, as you pointed out, that the latest cosmological simulations are not able to account for these galaxies. It goes too quickly in the real universe. No? They form far too quickly.
Yeah, it's true that we need like hydrodynamical simulations have the disadvantage that that can't simulate very large volumes. So it's true that they have the problem of volume and they might not be able to find them because they are very scarce as well. But still, there should be something there, and there is nothing after Redshift 4 very massive.
Yeah. Okay, thank you. Thanks.
Thank you, Gigi.
Thank you. I do not see any other questions or comments. So I would like to thank you once again and congratulate for the wonderful talk, as well as Eloisa. And I hand over to Giacomo to quit our today's session.
Yes, thank you. Thank you very much. Thank you, Dominica. Thank you, Paolo, for chairing the session, and thank you for the speakers from my side. They were very interesting work and very well presented. Congratulations. It's just to remind you that the videos will stay on YouTube, so you can watch them and send it around also other people. So they are, as a matter of fact, they are a material that will stay online. So this can be used and given to our colleagues, and it can be watched later. I would like to thank also people who participated. Thank you very much for being with us. This is very appreciated. Let me conclude by saying that next week we will not have the Hypatia Colloquium. We will have the ESO Cosmic Duologue, and in this it will be about the formation of the inner Milky Way. We will have Manuela Zoccali and Victor De Battista and moderator Elena Valenti from ESO. So we will have this next week, the duologue, and then we will start again with the Hypatia Colloquium again in April. With this, we can close, and thank you very much again, and see you soon. Bye bye.
Thank you. Bye.